We're here and we're talking about engine cycles. Geo's alive, he's awake in our class, or something close to that. Okay, so we've got engine cycles here. We're not going to get into the nitty-gritty of how they work or anything, but we're going to get into the kind of theoretical, where does an engine draw its energy from, and how do we kind of get those going. In general, we can kind of create a little picture or a diagram of an engine cycle. And this is for a heat engine. Refrigeration cycles get a little more complicated because there's like compressors and other nonsense in there. But for a general heat engine, this is what you need. You need, and this is in red because it's hot, you need a heat reservoir. This is something that has some energy to it. It's like the hot reservoir, as we'll call it. Okay? We can call this TH because it's at like some hot temperature or a high temperature if you wanted to. But it is some amount of energy you can draw from. Now, what happens here is we're going to pipe this energy down to our cold reservoir. Now, when we say cold, like, it doesn't have to actually make you, like, shiver. It doesn't have to be like ice. It just needs to be less than the hot. So if the hot reservoir is, like, 292 Kelvin, your cold reservoir could be 291. And that will work. It's not going to be as efficient as if having a larger temperature gradient or change, but it will work. Okay? Now, what's going to happen here is we're going to have some heat energy from that hot reservoir, and it's just going to work its way down to the cold reservoir. And this cold reservoir, it's at some TC for cold, or some people, and like I will write it as TL for low. Doesn't really matter. But that will have some low heat energy. Okay? Now, what also happens here is while some of this energy just goes from hot to cold, from high to low, some of it is going to be piped out. What we pipe out, this is the engine. And this is where we do useful work. That makes the world go round. That is what we care about. What this means in general is just by looking at this kind of diagram, you can make a mathematical equation out of it. You can say that the heat energy you had in the beginning, QH, if energy must be conserved, this has to equal the low energy, QL, plus some amount of useful work. Now, I did something really subtle here that you probably didn't notice, but I did it. What I just claimed here is that a heat engine, the work that it does is now positive. On our PV graphs, that was a negative value. That is the subtle change here. But this equation follows this diagram, and with this diagram, this equation is self-consistent. So that's a slight different sign convention I made there. Positive work is now that's work being done by the system, being done by the engine. That is positive work. Okay? Now, what we can also do with this is if we think back to what we first learned in our world of mechanics. Now, what we saw in mechanics last year was that the efficiency of a simple machine, often just written as E or EFF if you want to, whatever, however you remember that. An efficiency can be thought of as a work put into the system divided by a work you get out of the system. Now, we can actually think about that then as this W is the work we're getting out of the system. And what we're putting into the system is actually QH. With a little bit of clever algebra and moving things around, what we can do is we could write this equation as 1 minus QL, or the low heat of the reservoir, or the low reservoir heat, divided by QH, or the heat at the hot reservoir. This tells us the efficiency of our engine, and it is a very important equation for what we're doing. Now, there is one type of engine. Now, while this applies to any engine, there is one engine that is the most efficient. This is a PV diagram of what is known as a Carnot engine. Yes, it looks like Carnot, but it's not Carnot. It's Carnot. It's French. This is the most efficient style of engine, and it takes place because of the following. It begins with this curve going from 1 to 2. Going from 1 to 2, this is at the sum temperature T1. This right here is an isotherm. It is a region of a constant temperature. Note that even though this is an isotherm and the temperature is constant, there is some energy, some Q, entering in to this engine. Our next region, right here, this looks a little weird. This isn't just a left-right line for an isobar, and it's not up and down either for an isochoric or an isovolumetric. It's kind of curved as well, but it's not an isotherm. The temperature's changed. The temperature's gone from some T1 to some T2. This is what we refer to as an adiabat. This is an adiabatic expansion because the volume got larger here. Now, specifically for a Carnot engine, this engine needs to be done through a fully reversible process. So for a Carnot engine, this not only is an adiabat, but it's something known as an isoentropic system. And what we mean by a isoentropic system, or curve here, is that the entropy doesn't change. Now, as we're going to find out later, the entropy in the real world has to change. So the Carnot engine is really a theoretical engine. We can get things very close to it, but there's always going to be some entropy change, and therefore we never have a true isoentropic. In general, though, we'll just call this an adiabat. On the back side, once we hit some temperature T2, we go through another isothermal. Notice how this is still concave upwards on this isotherm. It's not as steep as the adiabat. It's a little more shallow, but it's still curved, concave up. Note that there is some heat energy coming out here. And then once we hit point 4 and we head back to point 1, we once again get our adiabatic, which is also, for a true theoretical Carnot engine, an isoentropic. This Carnot engine will create the theoretical largest amount of area between any two temperatures. That is the beauty of the Carnot engine. If you wanted to solve for the efficiency of a Carnot engine, you could actually take our prior efficiency equation, 1 minus QL over QH, the low and highs. But in this case, you can say that the efficiency equals 1 minus TL over TH. We don't have to worry about heats here because that isoentropic, those adiabats there, don't have any entropy shifts, so we can just use temperature. The trick to this, though, and what everybody will mess up, is these temperatures must be in Kelvin. If you're not in Kelvin, you're wrong. And that's that. If you're in Celsius, you can have a negative temperature in Celsius. 1 minus a negative number is a number greater than 1, which implies that your efficiency is above 100%. That's not a thing. Kelvin cannot go below absolute zero. Kelvin is what you want here. So this is the Carnot engine. Now, while this engine is theoretically the most efficient engine, we really don't use it for anything practical. The reason being is these isotherms, they traditionally happen slowly. This is a very slow engine that occurs here. Slow engines are efficient, but if you are trying to enter the highway and there's a semi coming up behind you, I don't want an engine that'll be like, oh, we'll get there eventually, because eventually that semi is going to come up and drive through my little car, and I'm going to be gone. I want an engine that when I hit that pedal, it goes vroom vroom, and I go zero, and I'm not crushed by the semi. If you didn't understand those onomatopoeias, go back to English. This is why we use internal combustion engines for right now. You can inject a bunch of aerated fuel in there. We can throw down pistons. We can burn that fuel, get the internal energy out of it, and we can get your cars moving very, very fast. Even better modes of transportation, though, are EVs, electric vehicles. Electric vehicles, instant transfer of power, which is what you want, and we're not going to get into this at all, but the drawback of a internal combustion engine is you have to shift gears. And there's some, changes to that given the cylindrical cones, or the cones that they make for the continuous gear transitions. But with an electric vehicle, you just spin motor faster, more energy, more current. And we talked a whole bunch about this when we did E&M earlier on in the year. You just dump more current through it, motor goes faster, car goes vroom. That's it. Instant. So EVs are even more powerful, to the point where even in like a lot of F1 racing, they'll actually have two kind of setups there. They'll have their standard internal combustion engine, but they'll also have an electric engine in there so that they can accelerate even faster coming off of corners and off their marks. So really interesting stuff within our actual real world. But while Carnot engines are hyper efficient, they're not very useful on a day-to-day application. But that's what we got to talk about from here, with just some engine cycles. These two efficiency equations, 1 minus QL over QH, and then for a Carnot, 1 minus TL over TH. This is what we'll be using. Until next time, this is finished. Adios, and take it easy.